On November 25th, 3i Atlas officially entered what observers quietly whisper about as the forbidden data zone, pulling familiar hypotheses one by one out of their comfort zone. From this point, a chain of clues about the geocode gradually comes into view. The geometry of lava tubes beneath the Martian surface looks like sockets pre-designed for gel structures. Sprites in Earth's middle atmosphere repeat the exact plasma motif observed around 3i Atlas. Artificial stars from laser guide systems accidentally weave a beacon grid around Earth. Suspected meteorites originating from Mercury carry patterns like gel frozen in place. And a thin plasma tube connecting Mars and 3i Atlas looks very much like a temporary data link. When all of these pieces are laid side by side, 3i Atlas no longer appears as just a strange interstellar visitor, but as a probe carrying the geocode quietly preparing for an experiment on Mars. The latest studies only deepen the questions: where did this star truly come from? Was it deliberately created by some unknown force? And what is its real purpose? All of those questions are what we're about to unpack step by step right now. "3i at last" is gradually moving into a region where the data is almost no longer accepted. Familiar physical models slip beyond the limits, and scientists begin to ring warning bells. At first, no one called it that. On the screens of the observatories, 3i Atlas was just a faint moving streak against the black canvas of space. But as it drifted deeper into the inner solar system, its orbital parameters, brightness curve, and non-gravitational acceleration began to show small, quiet deviations, subtle yet persistent, just enough to feel like an invisible hand was nudging the numbers. At Harvard, Avi Loeb watched the latest data stream in. The brightness faded more slowly than a typical comet, and the inferred outgassing forces did not quite match any standard sublimation model he'd used before. Loeb simply added a short line to his scientific notes: "Insufficient data to claim artificial origin, but cannot rule it out." In another quiet office, Michio Kaku reviewed the orbital simulations. Each time his team refined the parameters, the trajectory fit one segment and broke down in the next, as if 3 Atlas were deliberately slipping away from any explanation that was too simple. Teams at NASA ESA and independent researchers like Sarah Seeger kept a cautious stance, treat it as an unusual interstellar comet, but leave a small door open for something more. From that moment on, in the dim glow of control rooms, 3i Atlas stopped being just a lump of ice and rock crossing the sky. It became a gentle but persistent question, resting on the shoulders of modern physics. Beneath Mars, the lava tubes began to look less like caves and more like a frozen blueprint written in gel. For years, radar maps from orbiters like MRO had shown only long hollow tunnels under the Martian crust, ancient lava tubes, stable, dark, and once perhaps warm enough to shelter something more fragile than rock. When 3i Atlas entered the conversation, almost no one thought to place these two datasets side by side. Almost until a young researcher in Bethany Ehrman's team tried it as a simple shape recognition experiment. She applied the same morphological filters to two very different worlds: 3D models of Martian lava tubes and reconstructed surface maps of 3i Atlas, built from optical and infrared data. The result appeared quietly on her screen tube segments, with nearly constant cross-sections, rhythmic patterns of swelling and constriction, tiny junctions that formed repeating chambers and choke points. On 3i Atlas, shallow grooves and channels aligned in similar motifs, like a compressed version of the same soft architecture. When Avi Loeb reviewed the maps, he suggested a tentative name: GL code, not exactly life, not quite machinery, but a kind of geometric language for arranging matter into flexible modular structures that behave like gel. Bruce Joukowsky, more cautious, pointed out that flowing lava and melting ice are perfectly capable of creating repetitive structures without any guiding intelligence at all. Between those two positions, a grey zone opened. If 3i Atlas had passed near Mars in some distant epoch, perhaps it merely carries physical echoes of environments it has encountered before. But if there is any deliberate design involved, then the lava tubes under Mars start to look uncomfortably like a standardized socket system, an infrastructure already shaped and waiting for something gel-like to arrive, plug in, and begin to operate. High above thunderstorms, Earth's sprites trace fleeting circuits that strangely echo the plasma patterns around 3i Atlas. In the thin air of the mesosphere, 50-90 kilometers above the ground, sprites bloom for only a few milliseconds, red branching flashes shaped like upside-down trees or ghostly jellyfish. For atmospheric physicists such as David Sentman and Yoav Yair, they have long been a rare window into the boundary between atmosphere and space, where electric fields, plasma and gravity waves quietly intersect. When 3i Atlas drew global attention, a small ESA team decided to run the same morphological algorithms they used on cometary plasma data over high-speed sprite imagery. They did not expect much, yet the pattern that emerged felt uncomfortably familiar. A vertical central trunk layered horizontal branches and a faint crown of light at the top, the same basic geometry seen in simulations of plasma field lines around 3i Atlas as it passed through dense regions of the solar wind. Avi Loeb treated this as a suggestive clue. Perhaps nature, when placed under similar electromagnetic conditions, simply draws the same geometry again and again. Skeptics insisted it was nothing more than visual coincidence. Between those views, one quiet idea lingers. If 3i Atlas is some kind of machine, Sprites might be unintentionally revealing how it reads and writes into the atmospheric circuits of worlds with a sky. From the perspective of 3i Atlas, Earth's laser artificial stars can look like a beacon network switched on just as it passes by. At first, laser guide star systems were purely technical tools. At observatories like Keck or the Very Large Telescope teams, led by scientists such as Claire Max, fire amber laser beams into the upper atmosphere, creating fake stars, so adaptive optics can correct for atmospheric distortion. On the ground, it is nothing more than a clever calibration trick, no mystery attached. But when one analysis team overlaid the trajectory of 3i Atlas with the positions and operating schedules of major observatories, something unsettling appeared. During certain key intervals, 3i Atlas occupied regions of space from which it could see several laser guide stars above Earth at the same time. From its vantage point, Earth did not just shine with reflected sunlight, it was dotted with monochromatic points that blinked in and out following the observing cycles of human astronomers. Avi Loeb quietly noted that for a sufficiently sensitive detection system, such repeating structured light could act as a positioning grid, almost like we had accidentally built an optical lighthouse network around our planet. More conservative researchers argued this was nothing more than a scheduling coincidence, a side effect of busy observing calendars. Still, the question hangs in the background: if 3i Atlas is some kind of navigation device or probe, are we unknowingly broadcasting our location to it with the very laser systems we designed only to see the universe more clearly? In a handful of suspected Mercury meteorites, the rock looks less like solid stone and more like gel that has been locked in place for billions of years. On lab benches far from any observatory dome, thin slices of meteorites, some tentatively linked to Mercury's crust, rest under electron microscopes. Planetary scientists like Harry McSween and Lionel Wilson study their unusual chemistry, high metal content, odd silicate phases and textures that suggest they once formed deep inside a small, intensely heated world. Under high magnification, a different kind of pattern sometimes appears: rounded pockets, with smooth boundaries inside them, a fine web of microchannels, as if droplets of something soft had been frozen mid-flow. When data from 3i Atlas became available, a small group working with synchrotron-based spectroscopy tried an experiment that sounded almost whimsical: compare the microscale absorption patterns in these meteorites with the sub-kilometer texturing inferred on the surface of 3i Atlas. The match was not exact. Nothing in geology ever is, but certain motifs repeated: grain, boundary, network, the same basic triad Loeb's team had started calling part of the GL code. Some researchers suggested a simple explanation: given enough time, similar thermal and mechanical processes will sculpt matter into similar shapes, whether in Mercury's crust or on an interstellar body. Others were less sure. If 3i Atlas has wandered through many planetary systems, it might carry a layered record of environments it has sampled, with patterns like these acting as a kind of physical memory. Between those views lies a quiet possibility. Perhaps these Mercury-like meteorites are not evidence of design at all, but if any intelligence ever did shape matter using a gel-like architecture, this is roughly what its fingerprints might resemble once they have turned to stone. Near Mars 3 Atlas seemed to pause just long enough for its orbit to shiver, and for a thin tube of plasma to stretch between comet and planet. On paper, its path was supposed to be simple: a clean hyperbolic swing past Mars shaped only by gravity and a bit of outgassing. But when orbital dynamicists at JPL and ESA overplotted the tracking data, a small stubborn discrepancy appeared around the time of closest approach. The velocity relative to Mars dipped slightly below what their models preferred, and the inclination angle shifted by a fraction of a degree, tiny but persistent across different fits. At first, the team blamed normal culprits, patchy jets of gas from sunlit regions, uncertainties in the solar wind instrumental noise. Then someone brought in data from MAVEN and other spacecraft circling Mars. During the same window, the Martian ionosphere showed an odd elongated enhancement, like a filament of charged particles briefly connecting the upper atmosphere to a point in space that just happened to lie along the line to 3I Atlas. In simulation, when plasma physicists tried to reconstruct the event, a familiar geometry emerged, a narrow conduit of plasma stretched between the object and Mars, reminiscent of an oversized sprite frozen in slow motion. The field lines wrapped around 3I Atlas in a pattern uncannily close to what earlier models had shown in the solar wind, but now anchored at one end to a planetary atmosphere. Some researchers quietly wondered if 3I Atlas might be sampling the Martian environment, using the plasma tube as a temporary data cable. Others preferred a quieter explanation, perhaps it was only a transient magnetic connection, no different in principle from those seen between the Sun and its planets. Between these interpretations, the anomaly remains. The orbit did wobble, the plasma did form a bridge. Whether that bridge was a mere accident of fields and particles or a deliberate handshake still lies beyond what the data can comfortably say. In the end, 3I Atlas begins to look less like a stray comet, and more like a probe carrying a gel code quietly eyeing Mars as its next experiment. Laid out side by side, the fragments form a suggestive pattern. Beneath Mars, lava tubes resemble ready-made sockets for soft modular structures. High above Earth sprites sketch the same electric geometries seen in plasma around 3I Atlas. Laser guide stars accidentally build a lattice of artificial beacons. Suspected Mercury meteorites preserve textures that look like gel arrested mid-flow, and near Mars a brief plasma bridge links object and planet, while the orbit twitches in a way no one fully likes. Avi Loeb is willing to say that if a distant civilization wanted to test architectures based on gel-like matter and fields, it might search for worlds exactly like Mars-sheltered subsurface cavities, traces of water ice, a thin but responsive atmosphere, and a nearby planet Earth helpfully broadcasting its presence with coherent light. Others caution that nature is adept at repeating itself, and that similar shapes can arise from similar physics without any mind behind them. Between these two views, 3 Atlas drifts on indifferent to debate. If it is a probe preparing an experiment on Mars, the setup may already be underway. If not, it has still forced human eyes to look at their own system, as if it were under quiet examination. When something strange appears in the sky, astronomers expect the clearest answers to come from official observatories. For the interstellar visitor 3I Atlas, the first public images released by large agencies looked soft, pale, and oddly quiet. Meanwhile, small observatories and backyard telescopes recorded Atlas with a sharp coma and a well-defined tail. In those independent frames, a narrow jet appeared to lean forward from the leading edge pointing along the path. The contrast between official releases and community images led researchers to wonder whether 3 Atlas simply challenged standard processing pipelines. Some suspected a cautious wish to avoid drawing attention to features that raised uneasy questions. Others blamed timing or calibration. As that gentle doubt settled in, Atlas quietly became a test of trust, asking who truly sees clearly when the sky misbehaves. In the official previews, the frames of 3 Atlas looked strangely washed out, as if someone had turned down the contrast on the sky. Bright stars were crisp, but the heart of Atlas seemed softened, its inner structure blurred into a gentle glow. In technical notes, agencies described routine processing steps, yet the unusual forward-leaning jet seen by amateurs did not appear or sat buried in noise around Atlas. Some quietly suggested that 3 Atlas had arrived during a period of ongoing instrument calibration, making conservative releases understandable. Others wondered whether the teams behind Atlas were simply buying time, waiting until every odd feature could be explained away. That quiet gap between what was shown and what was possible left a faint unease, a feeling that the story of Atlas was already being edited mid-flight. In the outer darkness, another visitor quietly entered the story, the massive body scientist labelled UN-271. While 3 Atlas traced a sharp path through the inner system, UN-271 moved slowly like a drifting shard of a lost world. Telescopes watched UN-271 begin releasing gas at distances where standard models said a comet should remain frozen and still. For researchers mapping coincidences, 3 Atlas and UN-271 no longer looked like separate curiosities, but 2 points on the same unlikely curve. If at last reshaped expectations about motion and precision, UN 271 pressed against our rules for heat distance and when a comet may wake. Together at last in the foreground, and UN 271 at the edge turned a handful of anomalies into the first outline of a larger pattern. In the deep cold beyond Saturn, UN 271 began to breathe long before any textbook said a comet should. Compared with 3 Atlas, which disturbed expectations about motion and precision, UN 271 disturbed expectations about temperature and silence. Observers saw UN 271 vent carbon monoxide, carbon dioxide and ammonia in a region where sunlight was weak and distant. Standard models tuned on familiar comets predicted dormancy there, so UN 271 forced quiet revisions at the margins of those charts. For scientists still puzzling over Atlas, UN 271 became a second piece of evidence that the solar system's outer rules were incomplete. The combined presence of Atlas close in and UN 271 far out suggested a system-wide tension, as if the sky were gently renegotiating its own laws. Within a narrow slice of time, 3 Atlas in the inner system and UN 271 in the deep outskirts began misbehaving together. In the span of a single decade, Atlas traced a sharp inbound trajectory, while UN 271 woke from frozen quiet near Saturn's distance. 3 Atlas challenged expectations about motion and jet geometry, while UN 271 challenged expectations about when a distant body should start venting gas. Models had treated such extremes as rare, isolated edge cases, yet both sets of edge conditions appeared in the same observing era. Some astronomers quietly filed the overlap as coincidence, while others suggested 3 Atlas and UN 271 were exposing blind spots in long-trusted predictions. The simultaneity carried a soft unease, as if Atlas and UN 271 were hinting that the solar system's script was still being rewritten. From there, attention drifted toward a broader question: how many such visitors and anomalies were passing unnoticed before Atlas came into view? For most of human history, the sky seemed to host only familiar comets bound to the Sun. Then within a few short years, astronomers logged 3 confirmed visitors from beyond Oumuamua, Borisov and 3 Atlas. The gap between such encounters had once been imagined as centuries or millennia, yet Atlas arrived less than a decade after the first detection. Some explained the cluster as simple progress, arguing that better surveys were finally catching what had always been there before Atlas appeared. Others proposed that the solar system might be drifting through a denser stream of interstellar debris, making visitors like Atlas temporarily more common. A quieter minority noted that 3 arrivals in such quick succession strained earlier probability estimates, nudging models toward a new baseline. In that reshaped landscape, 3 Atlas became the most scrutinized symbol of a sky that no longer felt statistically quiet. As anomalies accumulated, researchers realized that neat categories were no longer enough. 3 Atlas demanded humility. Data alone could not decide whether Atlas and its quiet companions were rare flukes or glimpses of a deeper pattern. To move beyond reflex denial or eager belief, 3 Atlas asked for a slower posture of honest curiosity. That meant labeling what was measured, what was inferred, and what was only imagined, even when answers stayed uncomfortable. In that clearer light, Atlas became less a threat to old models and more an invitation to rethink them. Even if every anomaly around 3 Atlas one day finds a natural explanation, the story remains unusual. The timing, the precision of the jets, and the layered coincidences keep Atlas far from ordinary textbook behaviour. Assuming a purely natural origin only shifts the mystery from intent to mechanism. In either frame, Atlas continues to signal that our current understanding is incomplete. Around Jupiter, the path of 3 Atlas crosses an invisible boundary, where the planet's gravity outweighs the Sun, a region known as the Hill radius. For a comet passing at random, skimming that boundary would be a forgettable coincidence within a broad range of distances. In trajectory calculations for 3 Atlas, the predicted closest approach to Jupiter falls almost exactly on that Hill radius shell. The solutions place Atlas around 53 million kilometers from Jupiter, matching the boundary within small error. Statistically, such a tight alignment for Atlas might occur only a few times in 100,000 encounters. The match does not prove deliberate targeting, yet the precision makes 3 Atlas feel less like a wanderer and more like a visitor arriving on schedule. To learn whether this rendezvous was inherited from a natural path or gently shaped along the way, the next step is to examine the course changes of Atlas near perihelion. Near the Sun, the path of 3 Atlas stopped resembling a simple curve drawn by gravity alone. Close to perihelion tracking data recorded a small but decisive change in speed and direction for Atlas. The adjustment nudged 3i Atlas just enough to keep the coming encounter almost exactly on Jupiter's Hill radius boundary. Natural tugs from planets can perturb a comet, yet they seldom arrange such neat course corrections at precisely the right moment. As solar energy rose, the measured non-gravitational acceleration of Atlas also rose and fell like a system responding to a control signal. At the same time, high-contrast images of 3 Atlas showed a narrow jet leaning sunward instead of streaming backward as a tail. Standard comets grow broad outward, pushed plumes, but Atlas carried a forward-pointing spray that lined up with the direction of travel. Together, the sunward jet and the Hill radius matching course change forced statisticians to reconsider how rare such a pairing should be. Some groups treated 3A Atlas as an extreme natural exception, blaming uneven vents of buried ice for the imbalance. Others noted that if a vehicle wanted to trim a path toward Jupiter, the amount and timing looked strangely suitable for Atlas. To test those competing stories, researchers turned from the motion of 3 Atlas to the spectrum of Atlas, asking what kind of material could drive such jets. When NASA's Mars orbiters turned their instruments toward the passing visitor, the light from 3i Atlas carried clues about its composition. Ultraviolet spectra suggested that metals in the plume of 3i Atlas did not match the usual balance seen in familiar comets. The inferred nickel to iron ratio around Atlas skewed toward mixtures that looked more like high-temperature alloys than the cores of icy rubble. At the same time, analysis pointed to only a small fraction of water, near 4% in the volatile content surrounding 3i Atlas. Most long-period comets in the inner solar system present far richer water signatures, making Atlas stand out even among rare visitors. Some teams proposed that 3 Atlas might be coated in material accumulated over billions of years in interstellar space, a kind of metallic dust varnish. Others quietly wondered whether Atlas resembled an engineered shell more than a loosely bound clump of ice and rock. The data do not confirm an artificial origin for 3 Atlas, yet they refuse to settle comfortably into standard comet categories. In that tension between spectra and expectation, Atlas began to feel less like a simple body and more like a long-travelled artifact waiting to be interpreted. The sheer scale of 3 Atlas sets it apart, with estimates placing Atlas at roughly 1 million times the mass of Oumuamua. Compared with Borisov, the second known interstellar comet 3, I Atlas, appears hundreds to thousands of times more massive, yet Atlas moves even faster through the inner system. Despite this weight and speed, the orbit of 3I Atlas runs in a retrograde direction, while hugging the ecliptic plane within only a few degrees. Instead of diving in from a random angle on the celestial sphere, Atlas threads the same thin band where the major planets circle the Sun. For many modelers, the chance that an interstellar object like 3I Atlas would both be retrograde and so near the ecliptic remained small but not impossible. Still, the combination of retrograde motion and nearly perfect placement in the planetary plane made Atlas feel more like a careful insertion than a casual pass. When 3 Atlas swung through perihelion geometry, added another coincidence by placing Atlas almost exactly behind the Sun from Earth's point of view. During those critical days, ground-based telescopes could not directly see 3 Atlas, and the most intense part of the passage vanished into glare. The probability of such timing for Atlas is again low, the kind of alignment that usually lives in footnotes and edge cases. To some, these layered alignments around 3 Atlas read as a stack of rare but natural circumstances. To others, they whispered of choreography. Either way, the stage was set for the next question about Atlas, centered on whether its powerful jets and brightening matched the available surface and mass. Near perihelion, observers watched 3 Atlas brighten faster than any comet on record, climbing in intensity, as if a switch had been thrown. Spectra showed 3 Atlas growing not only brighter but bluer than the Sun, an unusual colour shift for simple dust and vapour. To support such power, naturally models for Atlas required enormous active regions across the surface, far larger than the estimated body could provide. When researchers fed measured jet strengths into standard sublimation equations, the required area exceeded any plausible exposed ice on 3I Atlas. Simulations that tried to keep 3I Atlas intact had to push parameters to uncomfortable extremes, assuming buried reservoirs and finely tuned vents. In image sequences, the jets of Atlas appeared tightly collimated, maintaining orientation across long distances, instead of fanning outward as broad plumes. That behaviour made 3 Atlas look less like a tumbling snowball and more like a platform hosting a few concentrated outflows. Some teams argued that the tension between jet power and available surface meant the mass budget for At-Last was simply being misunderstood. Others noted that if the jets of 3I At-Last were controlled, thrust not chaos, the same acceleration could arise from far less mass. Under that alternative, 3 Atlas no longer strained natural physics. The strain moved to a different question, asking who or what engineered At-Last. As 3 Atlas moves toward Jupiter, the encounter no longer looks like a simple flyby skimming past a giant planet. Trajectory charts show At-Last entering Jupiter's hill sphere at high speed, a corridor where any smaller bodies released from 3 At-Last could in principle be captured. For mission planners on Earth, slowing a probe into Jovian orbit would demand a powerful burn. The same physics applies if At-Last were to drop devices there. Any hardware separating from 3 At-Last near closest approach would need to fire engines to bleed off tens of kilometers per second of velocity. In that frame, At-Last begins to resemble a courier sweeping past a deep gravitational well, offering a brief window for deployment. Some scientists stubbornly keep 3 At-Last in the realm of ice and dust, refusing to assign intention to orbital mechanics. Others cannot help imagining Jupiter as the true long-term target, a bright beacon visible across the galaxy long before Earth existed. From that perspective, 3 Atlas may have noticed the inner world late, if at all, passing our orbit as a secondary detail on its way to the giant. Polarization measurements added another layer of strangeness to 3 Atlas beyond orbit and jets. Observers found that scattered light from Atlas showed an unusually strong negative polarization, deeper than values recorded for ordinary comets. Even when compared with rare objects like Borisov, the curve traced by 3 Atlas sat off to the side as if carved on a different template. While teams were digesting that signal direction, maps showed Atlas arriving from a patch of sky close to the famous WOW signal region. In 1977, that narrow radio spike appeared once from that direction, then never returned, leaving no agreed-upon natural explanation. The angular separation between the WOW source direction and the inbound path of 3I Atlas sits within just a few degrees, with a chance alignment probability near a few in 10,000. Statisticians caution that such alignments occur without meaning, yet pattern seekers still return to Atlas wondering about messages sent and messengers arriving. Each time a new anomaly joins the list around 3 Atlas, the debate sharpens between coincidence and connection. For listeners following the trail, the combination of extreme polarization and directional echo turns Atlas into a quiet focal point for long-delayed questions. For many researchers, spectroscopy became the quiet acid test for 3I Atlas. If the jets of 3I Atlas are driven by sunlit ice, the spectrum should show familiar cometary gases expanding at thermal speeds. If the thrust from 3 Atlas comes from technological engines, lines may shift split or reveal unexpected molecules and temperatures. A single set of high-resolution spectra could in principle collapse entire branches of speculation about Atlas in one stroke. Waiting for those measurements, scientists speak cautiously, knowing 3 Atlas may either reinforce old physics or press it to evolve. Between those possibilities, 3 Atlas hangs like a question mark, turning every planned observation into a small vote for one story or another. For weeks, the astronomy community held its breath, while 3 Atlas vanished into the blinding glare of the sun. When 3 Atlas finally re-emerged in early November, the returning object did not look like the quiet speck that had gone in. Images showed 3 Atlas surrounded by a vast antitail, stretching away from the sun, and a separate smoky trail pointing in the opposite direction. Photometry implied that 3 Atlas had shed an extraordinary amount of mass during perihelion, far more than early models had dared to assume. Instead of calming down after the closest solar pass, Atlas seemed more awake, more agitated, as if the real performance had just begun. The geometry of the new jets around 3 Atlas, balanced toward and away from the sun, made simple one-sided venting harder to defend. In quiet discussion, some teams treated this phase of Atlas as the key to reconciling all earlier anomalies into one coherent natural story. Others saw the heightened activity of 3I Atlas as deepening the divide because every new image answered one question, while opening two more. Emotionally, Atlas now felt less like a passing curiosity, and more like a moving experiment continuing whether humans watched or not. From this restless reappearance, the narrative around 3 Atlas flowed naturally into attempts to explain such violence through fragmentation fireworks and cosmic self-sacrifice. When the new images of 3 Atlas spread through the community, one voice offered a bold natural script. Avi Loeb suggested that the violence around 3I Atlas could be explained without technology, through extreme fragmentation. In this view, 3I Atlas did not remain a single body, but shattered into countless smaller pieces near perihelion. Each fragment of 3I Atlas would expose fresh ice-releasing gas like overlapping fountains together, driving the enormous jets. The metaphor became a cosmic fireworks display, a comet sacrificing structure to match the observed mass loss. This suicide comet picture allowed models of 3I Atlas to reproduce the brightening and long jets without invoking engines. The scenario required debris from 3I Atlas to disperse so finely that no clear rubble trail remained. Some researchers found comfort in a narrative where 3I Atlas remained a natural object, however desperate the behaviour appeared. Others felt that forcing 3I Atlas through such a story said more about human attachment than about the visitor. From that divide, attention turned back to observations asking whether later data around 3I Atlas would support fireworks or reveal something more persistent. When a South African radio array tuned its antennas toward the region of 3I Atlas, the spectrum revealed familiar fingerprints. In the data, astronomers saw absorption lines from hydroxyl radicals, the classic daughter products of water, broken apart by sunlight. For many teams, this OH signature wrapped 3I Atlas in a comforting label, a comet shedding water vapor as it rushed through the inner system. News summaries framed Atlas as a volatile, rich body finally behaving in line with the long-period comet expectations. For a brief moment, the discovery seemed to steady the narrative, giving 3I Atlas a place inside established categories. Papers and internal notes described Atlas with renewed confidence, as though the visitor had agreed to play by known chemical rules. Yet beneath that reassurance, some researchers remembered how many other aspects of 3I Atlas refused to conform. Hydroxyl alone could not explain the jet geometry, the mass budget, or the razor-precise encounters already mapped for Atlas. The detection solved one piece of the puzzle, while leaving the overall picture of 3I Atlas restless and incomplete. From that partial comfort, the community turned back to imaging campaigns, searching for debris and structure that might confirm or contradict the new comet label. When new optical observations arrived in early November, they brought an unexpected silence in place of the rubble many had imagined. If 3I Atlas had truly detonated into countless fragments, as the fireworks scenario described wide-angle fields should have shown a drifting trail. Instead, deep images around 3I Atlas revealed sharp jets and smooth halos, but no dense wake of broken shards peeling away. The region behind Atlas looked more like the flow around a still coherent body than the wreckage of a shattered core. Modelers revisited their simulations and found that a fully dispersed debris cloud from 3I Atlas ought to leave clumps and streaks bright enough to see. Those signatures failed to appear, leaving the mass loss of 3I Atlas without a convincing source in obvious rubble. For supporters of the natural fragmentation view, this absence became a delicate problem, pushing parameters for Atlas toward more contrived dispersal schemes. For others, the clean surroundings of 3I Atlas quietly strengthened the alternative picture of controlled outflows from an intact structure. Emotionally, the sky seemed to refuse easy closure, keeping Atlas poised between dying comet and functioning device. From that unresolved scene, attention turned to scheduled high-resolution campaigns, hoping the next close approach of 3I Atlas would break the tie. Against the backdrop of missing debris, an unsettlingly simple alternative took shape for 3I Atlas. Instead of a chaotic spray from countless fragments, the jets of 3I Atlas could be the exhaust of a controlled propulsion system. In that scenario, concentrated thrusters on 3I Atlas would direct outflows along narrow channels, explaining the tight, persistent collimation of the jets. Chemical engines or more exotic drives could deliver the measured acceleration with far less expelled mass than natural sublimation demands from Atlas. Calculations showed that if the jets of 3I Atlas were engineered, the energy and mass budgets would relax instead of strain. A small number of efficient nozzles on Atlas could generate the same push that natural models require from unrealistic surface areas. This framing kept the body of 3I Atlas largely intact, turning the visitor from a self-sacrificing comet into a functioning craft. The same data that forced contortions in fragmentation models suddenly fit neatly when viewed as deliberate thrust from Atlas. Many scientists resisted this leap, reminding colleagues that extraordinary claims about 3I Atlas require extraordinary proof, not just elegant arithmetic. Others admitted quietly that the propulsion picture felt oddly straightforward, making Atlas look less like a victim and more like an actor. Between those reactions, the community's mood around 3i Atlas began to split, and the silence from major agencies grew heavier. From there, the question shifted toward how openly current observations of Atlas were being shared, and what future data might be held back. As weeks passed after the Mars flyby, the public data stream about 3i Atlas thinned instead of growing. Ground observers knew that multiple spacecraft and telescopes had watched Atlas closely, yet new releases arrived slowly. Conference talks referenced ongoing analysis of 3i Atlas, while published plots lagged behind the observing calendar. For a visitor this unusual, the silence around Atlas became as noticeable as any spectrum or image. Some researchers assumed that teams studying 3i Atlas were overwhelmed sifting through a flood of measurements. Others wondered whether certain results about Atlas had been flagged as ambiguous or disruptive to share. Inside that uncertainty, theories about 3i Atlas hardened into camps, each group leaning on a different subset of partial information. The absence of clear unified statements about Atlas made the scientific process look stalled even as telescopes kept gathering fresh light. Emotionally, the sense grew that 3i Atlas was not only splitting explanations, but also exposing tensions about how knowledge is released. From that uneasy stalemate, attention turned toward the next dates on the calendar, when Hubble and Webb would take a closer look at Atlas. The trajectory of 3i Atlas brings the visitor to its closest approach to Earth. For the first time, Hubble and Webb will both turn toward the same interstellar guest, treating 3i Atlas as a forensic subject. The observing plan focuses on resolving the fine structure of any debris mapping faint trails that may surround 3i Atlas after perihelion mass loss. If wide fields reveal clouds of fragments, the cosmic fireworks model gains footing, presenting Atlas as a natural body in slow collapse. If instead the images show a sharply defined core with few or no fragments, 3i Atlas will push comet interpretations past their comfortable edge. High-resolution spectra from Hubble and Webb will also probe jet composition and velocity around Atlas, searching for subtle chemical or thermal outliers. Consistent signatures of familiar volatiles at expected speeds would support a chaotic but natural engine operating within 3i Atlas. Unexpected temperatures, narrow line structures, or unusual molecules could move 3i Atlas toward the margins of what standard comet physics can absorb. For many teams, the 19 December campaign turns 3i Atlas into a kind of cosmic autopsy, performed while the subject is still in motion. Every pixel and spectral line from Atlas becomes a piece of tissue cross, checked against models that either preserve or surrender old assumptions. Quietly, researchers recognize that even a clear verdict may leave 3i Atlas half inside and half outside existing categories. In that possibility space, the date feels less like a final judgment on Atlas and more like the opening statement of a longer debate. By late 2025, 3i Atlas stands as a living contradiction hanging in the dark between worlds. 3i Atlas bleeds water like a comet, leaving hydroxyl fingerprints that match the chemistry of familiar icy bodies. At the same time, 3i Atlas moves with the precision of a craft threading hill spheres and ecliptic planes, as though following a quiet flight plan. Jets from 3i Atlas should tear a fragile nucleus apart, yet observations show a coherent core instead of spreading wreckage. Brightness curves for Atlas demand immense natural venting, while images hint at narrow, disciplined outflows more fitting for engineered nozzles. Every attempt to place 3i Atlas fully inside the comet box pushes some parameter to an uncomfortable extreme. Scientists who favour natural explanations see 3i Atlas as a stress test for models a chance to upgrade comet physics. Scientists willing to entertain technology see Atlas as a proof of concept in waiting a possible machine disguised as ice. Neither side has evidence strong enough to close the case, and 3i Atlas drifts on between their sentences, in long, slow nights at observatories 3. Atlas becomes a mirror more than a mystery. Atlas reflects the human wish for company in the cosmos, and the equal fear of what company might mean. Atlas reflects our habit of forcing new data into old stories, and our rare courage to rewrite those stories. Future campaigns will sharpen numbers, spectra, and images around 3i Atlas, but certainty may still remain just out of reach. Long after Atlas fades beyond our instruments, other visitors will arrive carrying new contradictions of their own. When that happens, the memory of 3i Atlas will linger as a first rehearsal, a time when one distant traveller quietly revealed how incomplete our understanding of the sky had always been. By the time the datasets are archived and the telescopes turn to other targets, 3i Atlas will already be fading back into the dark. In the official logs, 3i Atlas will appear as another entry in a catalogue, a sequence of numbers and light curves buried among many. Yet behind those numbers, 3 at last has already stretched the imagination of the species that watched it pass. Within a single season of observing 3 Atlas forced astronomers to redraw quiet assumptions about motion composition and coincidence. In seminar rooms and late-night control centres, 3 Atlas pressed scientists to separate what was truly measured from what was only hoped for. Some will remember 3 at last as a severe teacher in comet physics, a case study that exposed the limits of old models. Others will remember at last as a possible messenger, a candidate craft gliding along a path so precise it felt intentional. Neither memory will be entirely wrong because 3 at last has always lived in the tension between those readings. Long after the last spectrum of 3 at last is taken, the methods built to understand at last will survive. New algorithms, new survey strategies and new instruments will carry the imprint of at last into the study of other skies. Each fresh anomaly will quietly echo 3 at last, whether or not its name is spoken. On distant nights, when another pale point begins to bend, predictions teams will reach back to the lessons of 3 at last. They will recall how at last demanded humility, how at last showed that even careful statistics can hide entire families of events. They will remember that Atlas turned silence itself into data when the lack of rubble or rapid disclosure shaped the story. In the end, 3 Atlas may remain undecided, never pinned firmly to the label of comet or craft. That open verdict leaves at last in a softer place, as a reminder that the universe need not resolve every question on human timescales. In that unresolved space, 3 at last becomes a gentle companion for the species that watched and wondered, then finally closed their eyes while the visitor kept travelling on.